The objective of this work is analysis of the morphology, chemical structure, and electrical resistivity of tin oxide film synthesized by sputtering on pit at different deposition times. This film can be applied in photocatalysis, gas sensors, and solar cells. PT was used due to low cost, flexibility, and transparency. Different deposition times were used because in temperature-sensitive substrates, it's important to control the heating of the polymer, which can be done by the control of the deposition time. For the synthesis of tin oxide films, a tin electrode and polyethylene terephthalate substrates were used. The films were synthesized with sputtering. In this technique, a plasma is generated. The plasma ions are accelerated towards a metallic electrode, ejecting their atoms, which are deposited on the substrate. The conditions for the synthesis of the films were an oxygen-argon atmosphere and deposition times of 30, 60, 90, and 120 minutes. The obtained materials, in the obtained materials, the morphology was analyzed using SIM. Their chemical structure was analyzed using XPS, and the sample was analyzed without erosion and with argon ions erosions of 30 and 60 seconds. And their electrical resistivity was analyzed using the 4-point method. According to the micrograph, the surface of the film is smooth with fractures. The thickness increases from 0.37 to 0.66 micrometers, with increasing deposition time. It can also be observed that the deposition rate decreases from 12.3 to 5.5 nanometers per minute as the deposition time increases. In the chemical structure by XPS, in the case of the film obtained at 30 minutes at 0 seconds of the erosion, the orbital tin 3D was adjusted with 3 inner curves, which correspond to 3 chemical states. They were assigned using the stoichiometry radio X, which indicates the number of oxygen atoms per tin atom. For this, the reference line on the right was used. The first chemical state has an orbital energy of 484.8 electron volts, which is located on the reference line and can be seen to correspond to an X of 0 or metallic tin. The state with the highest participation has an orbital energy of 486.2 electron volts. It was assigned to an X of 1.3 with 91% of participation. The third chemical state has an orbital energy of 488 electron volts that correspond to an X of 3. A similar procedure was carried out on films obtained at 60, 90, and 120 minutes. And in the figures, we can observe the percentage of participation as a function of the erosion time for the 3 chemical states found in each of the films. For the first chemical state in the 30, 90, and 120 minutes films, the state practically does not change and corresponds to an SnO0 or metallic tin. The percentage of participation at the different erosion times tend to be constant. In the 60 minutes film, the state corresponds to an SnO0.94, which is close to SnO, where tin has a valence of 2, and its participation increases from 5 to 10%. The state with the highest participation in the film is shown in this graph. At 30, 90, and 120 minutes, the state practically does not change and is close to the SnO 1.5, with a participation of more than 90%. The percentage of participation tends to be constant at the different erosion times. At 60 minutes, the state SnO2 is present, and the T valence is 4. The participation decreases with increasing erosion from 88 to 83%. In all the films, the chemical state SnO3 is forming, so we found a valence of 6 for the tin. It is possible to observe that the participation percentage practically does not change with erosion. The films presented electrical resistivity of the order of kilo-ohm, being higher for the films obtained at 30 and 60 minutes. In conclusion, the films presented 3 atomic oxidation states with atomic radius close to 0, 1.5, and 3. A valence of 6 was observed for tin, which has not been reported before. The electrical resistivity was in the 1.09 to 3.89 kilo-ohm per centimeter interval. Thank you for your time.